Um, so for the second session, I am mostly gonna spend time on like examples, like a case study, and we actually have and I'm mostly gonna talk about face detection, which I think, in my opinion, at least, it's a pretty fun problem, and maybe you'll enjoy it as well. But also, we have a talk by a speaker tomorrow or some maybe today, I forget, on the face detection actually the ethics of face detection. So so today I want to give you the. I'm not going to talk about ethics that much, just the how to do it using neural networks, and we will use this example. With this example, we'll try to learn more. Since we've already seen the fundamentals today, we were today this one earlier. Here in this session, we'll be talking more about some practical stuff, but obviously pretty important ones as well. All right, maybe any questions so far from previous session? Anybody? Any burning queries? All right, let's move on. Okay, yeah, I'll try to upload this when I can. Um, okay, so this, is hopefully this is pretty simple to understand what's going on. Uh, on the left, we have people, it's the same people, but different sort of faces taken at slightly different settings. On the right, we have different people. Yeah, different people essentially. And so basically on the left, we have matching pairs of faces, and on the right, we have not matching pairs of faces. Yeah, it's pretty simple, right? Nothing surprising. So, so when talking about face detection, actually, maybe the term I'm using could be slightly wrong, but there are two things to remember. There are two problems. First, you have to maybe correct. I should have said this face classification, because first you have to, in an image, learn to detect where there is a face. Actually, I think that is the face detection problem. I'm today I'm talking more about the face classification problem or face matching problem. And the second problem is the face matching problem. These are slightly different things, because imagine, let's say, I take just a big picture of the entire room and there are a few people there. I think it's really hard for a classifier to work at that level. Usually how the face detection works is first a classifier detects bounding boxes around the faces, and then like tagging, just use in Facebook or Instagram, right? That also, or when you're trying to take a picture with your phone, it does a bounding box detection of the face, and only once you have the bounding box, then you can do classification. Well, this particular data set I picked up for these examples is actually like a very simple kind of data set, right? Obviously I cannot train models and show you crazy examples at the scale of Facebook, not surprisingly. Um, and yeah, it's from this data set from Tufts University. It's actually free to download. You can do it as well. It's a really These are really nice, in my opinion, easy to learn sort of like examples, because you can see these are uh, images are taken, I think, here in two different format. One, uh, the same person is looking sort of at the same place, and just their expressions change. This is a good example where this lady's her eyes are closed, and here her eyes are open. Uh, yeah, and but there's no big change in other things like pose, lighting conditions, background, so many other things. So it's an easy starter kind of problem data set. If you work in very complex stuff, I think it's harder to solve. Obviously it's doable with a lot of data and good training, but yeah. So now you may let me ask you a question. So Facebook does, face classification, right? Like it detects faces and it does classification. So what do you think Facebook is doing? Like, let's say, how many people do you think use Facebook in the world? 1 billion, 2 billion? What do you think? let's say 1 billion, just for the sake of this conversation. Do you think Facebook has a model with 1 billion outputs as a classifier, like a softmax layer with 1 billion outputs in the end? What I mean, why do you mean, why not? Can somebody tell me? Why would that be a very bad idea? Yeah, every time a new person comes, you need to make a completely new model with billion one outputs, right? So it's just really nonsensical to do this. So how do you think uh, Facebook or anybody would develop like a model? What would be the strategy? Since it's we've discussed, it's silly to build a pure classifier of that nature. Does anybody have an idea? Yeah, that's a very good idea. You can certainly, so if you, well, you I mean, I don't think they do, their algorithm is clustering for something like Facebook, because with clustering, right, to do clustering, what do you need? You need a nose enough. We've talked a lot about this in previous sessions. It comes up again and again. You need a nose enough distance, right? So how do you, are you all familiar with k nearest neighbors? Yeah. Let's say we're doing k nearest neighbors in two dimension, xy dimension. Obviously the notion of distance is pretty obvious. It's the Euclidean distance between 2 points, right? But now you want to do clustering of faces. Again, it's a very difficult problem. You just take the difference between one face and another, and you take the absolute value. I think it will mostly give you nonsensical answers. So what do you need to be able to do to cluster faces intelligently, or any signal? Does anybody have an answer? You need to, sorry, somebody had an sorry? Featureization? Yeah, that's a very good, that's the answer. Basically, you need to project the face in some geometry, or using neural network or whatever method. You need to make like something that represents a face, like a feature, and these features should be such that faces that are similar are, and in the feature space the distance is low, and the faces that are far apart the distance is far, and then you can do clustering. Now if you have a well defined distance metric on this space, in this, let's call this a face space, right? So I don't know exactly what Facebook does, but I'm pretty sure it does something like this, where you have a, they have a really nice model that can generate like this feature for face, or in many sort papers and literature you'll find the word embedding. That's a term that's used often, if you've heard of embedding. So every, now let's say I take a picture on Facebook, and then they try to tag people. I think likely what happens is there are already template embeddings, because you're already in their system. They have already calculated your embedding for the first time, because the very first time it gets wrong, it just tries like random friends or something, I believe, uh, or then it pulls the embedding from your friend's profile picture or something like this, right? Very first time. So it already has a bunch of templates. It already has you like in its database. But it's much easier to have a few templates, representative templates, than just store hundreds of images per person and then search the entire database, right? Then it'll calculate distance in that with that template, and yeah. Does that make sense? Is this really confusing? So the main thing to remember is, it would be silly to build a classifier, because as you correctly pointed out, every time a new person comes, it's just like pointless. So what you want to try and do is actually build this thing called an embedding, or just learn features. Uh, yeah. I mean, what you could start with is, have you heard, how many of you have heard of the term transfer learning? Um, so could somebody tell me, what can you do some kind of transfer learning, even if you're just using classifiers, and solve this problem? Is anybody? Yeah, here. If there's a mic nearby, the second row.
This looks like the image classification problem. And I think the concept of transfer learning, we can use transfer learning approach in this problem. Is as far I know, there is a data set called ImageNet in Google, which is already trained on lots of images found all around the world. And our model launched the basic concepts from that layer, and we unfreeze the top layers and train the top layers on our data set. And from few data set as well, we can get a pretty good result using transfer learning.
Yeah, that's very good. That's exactly how you do transfer learning. But for this problem, specifically what you would have to do, you could try is, let's say Facebook does training like classification for 1,000 people or uses ImageNet. You still want this idea of distance, because you cannot ultimately train a classifier with billion parameters. But let's say your feature could be a trained model like a VGG or whatever, Inception, ResNet, whatever you want, whatever you pick. It's been trained on ImageNet. The top layer before the classifier layer, you can take that, and that could be your feature. Can anybody guess what would be a problem with that? Actually, she already mentioned. She said you said you then tune it on our data, right? Without tuning it on our own data, it may not work very well. So you still need to tune it a little bit, because what works on just random natural images may not work very well for faces. However, you can, let's say, start with this ImageNet feature, and then you can train a model on faces. Let's say now you only classify 1,000 faces. You build a classifier for 1,000 random faces, or maybe some kind of representative faces across maybe all over the world. You sample equal across many countries, so you get different kind of faces. Now, then if you do some fine tuning on this 1,000 face classifier, then again, at the end, you just take the last top layer, and that could be your embedding or feature. So then when you see a new face, you still pass it through this model, but you don't do classification. You use this feature to do clustering or compute between templates, whatever. Yeah, is this concept clear? Or we'll discuss more. Let's not get stuck here in just this one slide. Okay, yeah. So again, I think the correct term should have been face classification, but it doesn't matter. Like, we don't need to get hung up on terms. The face detection, yeah, it should be resilient to change in pose, facial expression, right? Somebody smiling and not smiling, it's still the same face, right? Lighting conditions, like I talked about the cat earlier, bright outside, dark inside, still should be able to do. Background, somebody takes a nice photo in a studio with a white nice background versus just a room with random objects, you still want it to work. Clothing item, hats, sunglasses. Actually, this data set will be made, there may be examples later. This does have people wearing sunglasses as a example. And so I remember somebody asking earlier, I forget your name, but he asked, okay, will the network not forget like important things? And again, we come back to the same idea, with max pooling. We talked about how it learns translational invariance, and it learns to ignore unimportant things and emphasize important things. Again, this is a canonical idea in machine learning and deep learning, where you want your network to be invariant, resilient to many different changes. We only want our network to respond when the person changes. But if other things about the persons are changing, we want this network to ignore it. how to do that, it's not easy, it's hard. But that's what we should try to do. Okay, actually we discussed this already, you know. I asked about the Facebook example. Yeah, it just doesn't make sense to, I think, do this problem as a pure classification problem. um, so essentially we are here, actually we are doing regression, and we will do a we can still do classification then by thresholding on the regression, right? So what we're going to try to do is we'll take two pairs of faces, you know, faces that match and not match, and we'll try to regress the distance between them. So in the training data, faces that match will have distance. What should be the distance for faces that match? 0. Yeah, in training data it should just be, we're just going to make it 0. And for faces that don't match, what should it be? More, yeah, it should be more than 0. It could arbitrarily be anything, but we're just going to make it 1, because, you know, there's nothing, it's, yeah. Yeah, very good question. So I wonder if in different so I just I've seen a lot of just Euclidean distance, but I believe you could do cosine as well. I am in neural network, I haven't really seen cosine distance that much as a, but maybe there are. Me not seeing is not like disqualify. uh Yeah, so that's very good question. Yeah, so with cosine, you're guaranteed that, you know, the distance will be between 0 and 1. With Euclidean, there's no, you're not going to have a guarantee. But when you do the training, the loss is set up in such a way that your outputs will be generally pretty, you know, obviously will never be below 0, but it will not go too much higher than 1 as well. So you can set up the loss in such a way that that happens. So yeah, because otherwise if it's just going all over the place and higher than 1, the difficulty will be, where do you draw that boundary? Right, is it 0.5, the threshold for match versus not match? So but the loss is set up in such a way that you're not going to have this bad issue. Okay, does everybody understand what we're trying to do? Yeah, we are training a model that actually has 2 inputs, right? Not just 1. I mean, you can think of it 1 input as a pair of images or 2 inputs. And this model will output distance between the 2 faces. And this distance is not just some like basic, it is a learned distance that should be representative. And it's not just representative, it should be, there's another concept and term we use a lot, it should be discriminative. Well, obviously we should not discriminate between people, but I think we should discriminate between features, you know, if you want to do classification, right? If you've looked at whatever K and N, basically classification is essentially simply just drawing decision boundaries in high dimension. That's what classification is, right? um, it's that's what it is, you know. Yeah, I mean, and you want to draw these boundaries so that things that are similar are close to one another, and things that are far apart are separated out by these boundaries. That's essentially what all of classification is. Regression is the same, there's no difference. In regression there are no boundaries, but it's the same thing, you know. Things that are actually should be close should have small distance, and vice versa. So we always say features should be representative and also discriminative. Like if things, features of similar objects should also be similar, and vice versa. So yeah, this is a very simple diagram of what this sort of approach looks like, right? You still, so this is our 2 inputs, image 1 and image 2. We still have the same network. We still have, then we have a bunch of convolutional layers, and in the end we take features from here and features from here, and we just calculate distance between the 2 features, and this is your output. Now, one pretty important thing that we do here is we actually use the same weights for this side and this side. In fact, it's the same network producing two outputs on two images. Why do you think this is the case? Does anybody have an idea? And does anybody know what this sort of architecture is called? Any idea? Siamese architecture. Okay, wonderful. Wow, you should be teaching, man, not me. Okay, yeah, do you have any idea first why it's Siamese? Actually, maybe I don't know also, but I vaguely remember. And then why are we sharing these weights? Yeah, correct answer. Yeah, I think the Siamese comes from I think there's like this term called Siamese cats or something where I think it's Siamese twins. Siamese twins. Basically, it means yeah, same. You know, same. You know, like it's something like that. That's why, since you know, it's like this twin architecture. You know, it's the same weights. I think that's why they say it's Siamese. Yeah, thank you. Who said the Siamese twins? Thank you, Anissa. Okay, yeah. So yeah, let me emphasize that point again. So because we're operating on the same types of images, same image space, right? Like same type of images, it makes no sense to have two different types of network producing two different types of outputs. That's why we share the weights. Essentially, this is the same network producing outputs that then we compute distance between. Now, can somebody also imagine a scenario where we would not want this to be true, where this W it would be different, or it would be different? It would be same for some layers and different for others. Can you imagine? Can anybody imagine such scenario here? Since you so, what should be true for the converse to be true? You said because the images are from the same subspace, you want to project them into the same subspace, right? If your images are from different subspaces, then you should also handle them differently, right? Actually, ultimately, I guess you kind of want to do project them into the same shared subspace, but at the input layer, so if images are coming from different subspaces, you want to handle them, treat them differently. Where would such an example, what would be the sort of situation? Yeah, that could be, but generally, if that was the case, you would probably just convert the color to black and white. But that's a great example. It's something exactly like that. Let's say, because normally when you think of images, we just think your standard RGB, images with our phones and stuff. But there could be, let's say, satellite imagery with 7 different channels, or like infrared. There could be an infrared image and natural image. Maybe we want to make this classifier that can take either, works with both, or let's say there is in medical imaging, this can happen where you want to like do this sort of thing in images coming from MRI and images coming from CT, right? Images coming from CT machine and MRI machine, they are different kind of images. They're different. It's different subspaces. That's why you want to handle them differently. So maybe you don't want to share these weights. And at that point, maybe you wouldn't call them a Siamese network. But however, here, since we do this, we share all the weights, and essentially these are twins. The network is called a Siamese network. Yeah, so actually I haven't showed you the loss function, which is somebody brought up earlier. How does this guarantee that this loss is called a contrastive loss? And there's a little bit of similarity to the SVM loss. If people remember what SVMs are, and there's a concept of margin in SVM, and if you're within this margin in SVM, there's no penalty, there's no penalization. I think there's a similar concept here, and that margin is of 1 because we also want our output to go from 0 to 1, and there's some way that I forget the details, but that the contrastive loss helps you achieve this. I mean, I think it was a little bit beyond the scope, so I didn't put too much of that. But let's continue. But any questions so far? All right. So yeah, this is sort of like the ideal case. This is what we want, right? We have pairs of matching faces. The distance would be 0, right? And not matching 1. Obviously, when it actually trains and in inference, it may be so that this is like 0.1, 0.2, and maybe this is 0.8, or sometimes maybe it can even go maybe it's 1.1. I think it can happen, but essentially, but there should be things that match should be 0, don't match should be 1. So I actually trained 2 different kind of networks on this. And one, I made a custom network, very simple, bunch of convolutional layers followed by a few dense layers. And another, I did transfer learning. So we've heard a lot about transfer learning earlier. Somebody mentioned. So I actually did exactly what was kind of described earlier. I took a model that was pre-trained on ImageNet. Then I just added a few hidden layers on top of it. And I froze the model trained on ImageNet, which is actually, it's called MobileNet v3. I'll get into this as well later, but yeah, for now, essentially we're going to test 2 approaches, which is better to train something from scratch. Well, the caveat being, I did not have resources and time to train like a big model and fine tune it. I think ideally, if you really had the time, the data, and the resources, big GPUs, I would guess like a custom solution might win. But in the absence of that, even with like a CPU, your small laptop, this is a really great solution. And this is something I really want to emphasize to you all, that you don't need, the beauty of transfer learning is, even with less resources, you can, at least for some kind of classes of problems, you can solve interesting problems without needing extremely good resources. All right, let's move on. So couple, these are some very standard things that we do when we're training neural networks for computer, like for image-based tasks. I do a lot of data augmentation. So images are randomly translated, rotated, and flipped horizontally. The flipping horizontally here probably doesn't do that much, maybe just a little bit, because faces are pretty symmetric, and flipping the image probably, yeah, I don't think it matters that much, but I did it anyways. Another thing, so I didn't truly do this, but one thing to remember is, when you especially have a really large data set, this data augmentation should be implemented. You don't do data augmentation at the beginning and store all your augmented data and then start training the model. What you do is you do augmentation on the fly. That's what we call it. Your model training can be connected to this thing called a data generator that does the augmentation on the fly. So every batch that is generated is a augmented set on the fly, because you can, conceivably, you can do so many crazy augmentations, and you start storing all that in memory. You're never, that's just a crazy idea. You should never do it. So yeah, that's what you should do. I still load the original data in memory, but not the augmented data. But the truth is, you don't even have to load the original data in memory. You can do this thing called augmentation from directory. So you can directly run this on fly from like, data set that is just stored in the hard drive. You don't have to load it in your RAM. So you can do a lot of, that way it's obviously going to be a bit slower, right? because you're loading it into the RAM and in your cache or whatever, and then doing the training. But what I have is like an in between. I load the original data, which is quite large, but the later part I do it on the fly. So another thing is to avoid overfitting with neural networks. We already saw it yesterday. We had this thing called checkpoints. So we should use checkpoints where only the best performing models are saved and not the bad ones. And yeah, that's all. Let's just look at maybe. So my very first attempt, I didn't do any data augmentation, and the curves for training and testing look like this. So on the left, this is loss, and on the right, this is accuracy. So anybody tell me what's going on here? Like, is this good performance, bad performance? Huh? I mean, it's not like totally bad. Because you're still learning something, right? Even your validation accuracy is still at 0.7, like a little bit above 0.7. But what is going on here that is slightly undesirable? Overfitting. Who said overfitting? All right, can you explain why? Well, how can you tell there's overfitting? Mm-hmm. Yeah. Keep going down. Yeah. Yes, that is quite correct. Yeah, so it's always important to draw these two particular curves. It's You can just, even by looking at just you can, at least you should do one, because oftentimes these two are highly correlated, sometimes not. But you should always look at these two curves, and now you immediately realize, okay, there's a lot of overfitting. How do you correct this, right? Uh, there are many approaches. You can maybe train a simpler model, right? That's one way. Maybe you can train only for 2 or 3 epochs, right? That way you don't go to this big gap regime. This is a little bit of a gap, right? um, yeah, there are many different approaches, uh, but reducing, if you reduce the model size, your accuracy ultimately is also not going to increase, because you can only do so much with a simple model. So that's when you start thinking about data augmentation and other potential changes to the architecture that help you reduce overfitting. And one of the most simple thing like image classification is doing data augmentation. So I already mentioned, what I do is randomly translate a little bit, rotate a little bit, flip. Again, I don't have to write code that does this. It's so simple these days. Your libraries will already have functions where you just tell, oh yeah, do augmentation with some degree of translation, rotation, flipping, whatever. You can write your own function and provide that as well, if you know already a priori that there are some other interesting things going on. But if that is not the case, just use the standard ones, and you don't have to do anything. Yeah, it's a there is no free lunch, but maybe this data augmentation is a little bit free. All right. So with data augmentation, so what do you think is going on here? Somebody, is this good, bad, better, worse? No, why is it better? The gap between training and validation is much lower, right? So there is still a gap. I mean, some gap is very hard to avoid. Um, One thing, would you say, what is one thing that is maybe kind of a little bit bad about this? Too much, sorry? Yeah, it's a bit noisy. So you wouldn't, it seems like I wouldn't be able to say for certain that in the next one would it be here or would it be here. It could just be this, like, random, like, local minima where, okay, the accuracy is decent. So I would have maybe a little bit concern about the stability of this output, but in general, this is kind of smoother. But it's obviously not so surprising because, with the augmentation we're introducing kind of noise. So, but this model is learning to tackle the noise. That's why we have, we have these outputs. So these are just some outputs of the, I believe, the augmented model. So in terms of the pure numbers, it's just a little bit better, I believe, like 0.75, whereas it was just below 0.7. So it's not, just if I had stopped at epoch 2 here, the performance probably wasn't that bad, um, but there's a third thing to also think about, which is, because for this data set, the training and validation set is actually, statistically they're quite similar. It's coming from this very controlled, tightly controlled sort of like database where the conditions are so similar. It's not so shocking that you're going to get pretty good validation accuracy. What you really want is like a totally independent third party set, which is somewhat statistically different and more challenging, where you evaluate your model. So, and from that point of view, I would have maybe slightly more trust on this than, even though the numbers look the same on, let's say, like a totally like third party kind of data. I mean, this is not third party, this is still from the similar distribution, right? So this, so yeah, for the matching one, so I have both the matching examples, but it's matching pretty nicely. I mean, I would say this is kind of challenging. This guy's face is up here on the top, and he's also well, it's like cut off too, and this is very different, but it still does okay. But then there are some obvious like pretty pretty bad failure too. I mean, this is the same guy, but a little bit, the pose is different and the background changes a little bit. And I noticed that it was really sensitive to the background, at least in the beginning, before the augmentation. Uh, and actually, the very first time I tried this data set, the pose and the pose change and the facial expression change data was different. So when I first started, I only trained on the changing of the facial expression. Then only later I added the pose. So if we hadn't added any of the changes to the pose, this model would be even more useless. It would only be able to tell work, only when somebody's sitting very centered on the image. And basically it would only work on like passport photos, which the nice ones they make in studio with making everybody look very fair, which I don't know why they do, but they do. Anyways, jokes aside, yeah, well, yeah, but basically now, after adding these examples and so on, it's resilient, but it's still like failing in like obvious cases. Now I have some faces of myself and my friends, which were obviously not in the training data at all. And so as you can see, this is the same person, my friend, and with no augmentation, it was really bad. With augmentation, it has improved a little bit. This is myself. Um, Slightly different face images, but still like, I have some facial hair. Um, so it's not like totally different. Then actually I compared with my friend as well, and actually in the beginning it was saying it's the same person, well, and here too, but at least actually it seems the distance has gotten worse. So, well, and these distances this one improved, but this also got worse. So maybe with augmentation, I don't know, maybe it just got biased to saying more yes, I don't know. But I I I'll talk about a little bit the other approach that I took, and it works a little better with that. But essentially, so what have we learned here? Basically, you can have pretty good validation result, but when you apply it to the totally different kind of data set, right? Because the training and the validation for that set was essentially coming from like a similar sort of controlled setting, you know so today for lab, actually this is what I would like you to be able to do. I would like you to be able to train some models and put your own face and your friend's face and see if you can match your own face and be able to tell apart you and your friends. All right, so that's my hope. If people don't delete my data and notebooks, maybe it's possible. Otherwise, We'll see. God knows. All right, I'm kidding. I think maybe I deleted myself and I'm just blaming you all. Okay, so now we do transfer learning with MobileNet v3. How are we doing on time? I believe this is until 12, right? Okay. Uh, so with MobileNet, as the name suggests, is targeted for mobile phones, and it is meant to be really small and efficient. And I'm gonna go into the architecture of this a little bit in a little bit, but essentially you have to remember that it is very lightweight and small, which means I can load it in my like computer and like play around with it nicely without taking too much time. So so I take this and then I add two dense layers. I actually add the very same size dense layers earlier with dimensions 64 and 16, and I train a model. So this is the output. What can we see from this here? What can we infer? Have the accuracies increased a little bit or no? No? Yes. I mean, it was the best one earlier was 0.75 and now we have 0.8. Obviously, when you train until this many epochs, it seems like there's still overfitting, but barring that, this model, there's hope that this model will work better, right? Because the best accuracy here is 0.8 and earlier it was 0.75. Yeah. Okay, let me just show it to you if you're not convinced. Yeah, it reached 0.75 here also, and here just below 0.75, maybe 0.74. And yeah, and believe me when I tell you this, in the world of deep learning and computer vision, going from 0.75 to 0.8 is a big accomplishment. You'll get a big bonus if your classifier at job goes from 0.75 to 0.8. It'll be twice your dasai tihar bonus. Believe me, I'm not saying I didn't do anything personally very impressive. I just used a MobileNet, a pre-trained network that was already pretty powerful, right? But you may think, oh, 0.5. It's really hard to, sorry, 0.05 even, not even 0.5. 0.5 is crazy. Nobody does that. But yeah, improving by 0.05 is like, I'm not saying I did anything impressive again, just this model did. Yeah, and nobody's giving me bonus for this. but hey, look at this now. It correctly calculates. In fact, the distances are also better, and in the one where it's not matched, also it works. Obviously, there are some other examples. There were failures too, but I didn't show it to you. Why would I do that? I have to prove that I am impressive. But hopefully, in the lab today, we will get to do something like this, where you can play around with different images of yourself, your friends, and it would be cool what kind of failure modes we can detect. And I think it'll be hard to figure out and solve that failure mode in this short time, but we can try, if we reach that point. Okay, I just want to wrap up now in maybe well, actually, let me just pause here for some questions. Yeah, makes sense. How everything understood so far? So okay, maybe somebody since not you, since you mentioned that idea originally about ImageNet based transfer learning, why do you think that was helpful? Who has an idea? So why is that even helpful at all? What does pre-trained model with ImageNet giving us? Knowledge from previous models? Yes, that is true, but can you be more specific? Sorry? Facial features? So actually, well, ImageNet is trained on like everything, not just faces. It's trained on like natural images, just sceneries, cats, dogs, objects. There are 1,000 different categories. It's trained to correctly classify those 1,000 different categories. However, particularly in the earlier stages of a neural network, you're not really learning things that are super specific to the problem at hand. Like I described, showed you examples in the 1D convolution case, right? The first layers of features are just responses of edge detection, Gaussian blurring, flipping by multiplying by a negative number. So very generic things are happening in the first many layers. So if you take a model trained with ImageNet, the features you are going to get will also be similar. It'll be a bunch of it'll be more sophisticated than what we had with our 1D example. But you can imagine that yeah, particularly the lower level features are still going to be the same thing, and the success of you doing something interesting as opposed to training from scratch, particularly when you don't have a lot of data set and when you can't train like a big powerful model, is this alternative is that it's a safety, that you, yeah. But yeah, it is knowledge, but more specifically, yeah, these, you learn all these features, you get to use these features which are a result of learn convolutional kernels. Yeah, any other question? um yeah, cool. Okay, yeah, I'll move on. So yeah, we talked a lot about ImageNet. So what is ImageNet? So ImageNet, has anybody heard of the term WordNet? WordNet? Yeah, so it actually, ImageNet is modeled after WordNet. WordNet is like this online database where if you've done any intro to NLP sort of class, if you've done any like work, studied NLP, basically all the words, I suppose, all the words in English language, as far as they know, they, not just words, even things like terms in the internet and slangs and whatnot, they are classified in a hierarchical structure, in a basically like a tree-like structure, and that is called a net. Let's say you start with, everything is an object or an entity, right? You start like that, an entity. Now then you can describe what are different kind of entities. There are living creatures and non-living creatures. Maybe that's how you start. And what are living creatures? Maybe there are well, there are vertebrates and non-vertebrates. Now, what are vertebrates? Well, there are mammals and there are, I don't know, birds, non-mammals, right? I forget. Sorry, it's been a while since I studied biology. I actually didn't study biology even in 11 and 12. So yeah. Then finally, in the leaf, right? We all know how a tree structure works. In the nodes of, you will have a dog or a cat, or maybe it goes even further. Maybe there's all the breeds of the dog, right? There's a husky, there's a terrier, whatever your favorite breed is, right? Bhusia kukur, whatever. My favorite is definitely Bhusia kukur, but maybe yours is husky. I don't know. People. Anyways, so the same idea is emulated in images, and this is a pretty massive repository of 14 million images, organized in this sort of like hierarchical categories. Yeah, sounds good. And but the particular ImageNet, when people talk about ImageNet and the model based on ImageNet, what they're referring to not is this larger data set. They are referring to the problem and the data set for this challenge, the IELVSRC, which is something like image, something large scale, something I don't remember, but essentially it used to be held every year. This was a challenge where they make 1,000 categories selected out of all these other categories, and you basically build a classifier to categorize these 1,000 categories, and whoever does the best wins this challenge. And one thing to note is the errors are calculated, or the accuracy is calculated in two different ways: the top 1 error and top 5 error. Anybody knows what that is? Can you make sense from the words top 1 and top 5? So the I'll just say it. So the top top five. So actually the competition and the errors and accuracies is evaluated in based on the top five error or accuracy. And what that means is, if you make a prediction, and remember when we use softmax, we talked about this yesterday, right? There's a thousand output softmax, 1,000 dimensional output. It's a probabilistic output, right? So you take the max. That's the, if you just want a single output, you just take the max. But if you take the top five outputs, right? Top five probabilities out of the 1,000, you get the top five output from the model. And the accuracy is evaluated in such a way that if the true class was a husky, but your model says terrier, Busia, I don't know, Siberian husky, and Labrador. I don't know dog breeds, but you get the idea. As long as husky is one of the five, you're still accurate. So that way it makes it a little bit easier, and for a lot of practical applications, that's good enough as well. I mean, I suppose. Yeah, makes sense. Everybody understands the top one and top five accuracy, because that's how they report the results in many of the papers, and it helps to understand that. So the first model. So I'm going to talk about different architectures that were built through somewhat not so super recent history, but maybe like from like 2014 to like 2018, that sort of era, 2019. Past few years, there have been a lot of sort of other kind of development. These things called transformers. I'm not going to get into that. Maybe the NLP people will get into that more. But yeah. So the ResNet is actually a very simple change to the standard convolutional article. Sorry, not article. Convolutional network operation. There is just the only difference just in the main core different is there are these things called skip connections that map this input, this sort of output of this, let's say, layer here, and it does a addition. It does a yeah. So, and what that accomplishes, let me show you in a little bit. So, and that is repeated throughout the entire network structure. And what this does is, I'll talk about it in the next slide, but we're predicting the residual and not the sum, right? I'm going to get into how that works. But the motivation for, can anybody tell me, maybe, okay, maybe you don't know, but if anybody knows what's the motivation here? So if anybody's familiar, otherwise I can say, obviously. Yeah, exactly. Quite right. So as you know, people started getting really successful with deep neural networks, but they started reaching like a upper limit, as you see here in the, which one? So right is, actually both training error and test error. Okay, so these are training and test errors on CFAR10, which is actually a simpler problem than ImageNet because it's just 10 categories. It's some, I think you could say, I imagine if you've done any work with convolutional, you see the CFAR10 also pop up a lot. And in both cases, in the training and the test error, the model with more layers is doing worse, right? The 56 layer model has higher training error and test error as well. So it is a little bit perplexing, right? So initially they started getting really successful with building really deep networks, but at some point it started performing badly. So which is surprising because intuitively, let's say you have a network, you have a model with 20 layers. Let's say then you want to add like few more layers to it. In principle, the few layers can just learn the identity function. Does anybody know what the identity function is? Or identity mapping? Same, yeah, whatever is the input, you get the same output. You know, this model, new model with these few extra layers could trivially learn in these extra layers just identity, which means it does nothing extra. It just propagates what it had from the before. And it should in principle be able to output the same accurate result as the network with less number of layers. But in practice, they found that this was not the case. It didn't work like this, particularly because neural networks are optimized. You know, these are very non-linear functions, and the optimizations can get stuck in like bad, you know, local minimas. Yeah, and hence, and there's this. So there's also this. I mean, the vanishing gradient may or may not be totally correct, but that's the reason for vanishing. So the vanishing gradient was a big problem in the early days, maybe even prior to this. But they solved the vanishing gradient to a certain extent using batch normalization, if you've heard of that term. So in deeper and deeper network, you add this layer called batch normalization, where every output of a layer is normalized to have I think, you know, 0 mean and 1 standard deviation or something like this, right? Which is just a scaling for the most part. Yeah. Yes. Yeah. So essentially, in principle, it should not have been that way, right? Because I described, let's say you have a network with 20 layers. Let's say you just want to add 2 more layers to it and make it 22. In principle, this 22 layer network should be able to do as good as the 20 layer network, because the 2 extra layers should be able to just learn identity mapping, as in it does nothing. It does the same thing as the 20 layers had done. That's it. But in principle, it doesn't work like that. Why doesn't it not work like that? So does anybody understand the concept of convex optimization versus non-convex? Does anybody know what a convex function is? So, yeah, for a convex problem, convex function, yeah, there's a global optimum, there's a maximum or a minimum. So if we were doing convex optimization, that would be true. But when you're doing non-convex are also referred to as non-linear optimization. You don't know, particularly with gradient descent, you don't know what path this optimization takes. It's stochastic in nature. Anybody knows what stochastic means? It means it's somewhat random. You know, it's at every instant what exactly happens, we don't know, right? It will reach the generally the same area, but because of the stochastic nature, it's not a you. That's why in practice they found that they were having a lot of difficulties with deeper network. And yes, it's a little bit with the vanishing gradient, but the vanishing gradient was solved a little bit with batch normalization. But they speculated, this team who's developed resonance speculated that maybe there was something else going on. And their hypothesis is that it's for the optimization, it's easier to learn to predict 0 than 1. 1 is identity, like if we write in matrix notation, right? One, you know, identity map is just 1 on all the diagonal matrix, right? So that's why the hypothesis is that it's easy to fit like, you know, 0 than 1, and it's easy to fit a residual of a function. So way this thing works is there is x. This is output of a previous layer, and consider this a block, one single layer. Okay, just think of this as one layer, and the x is propagated here and x is added here. And what you learn here ultimately is f of x. So what you have in the end here is f of x plus x, right? So what you're learning is f of x. So this is slightly tricky. So what you really want to learn is h of x. And h of x is f of x plus x. But the idea is that it's easier to learn just f of x than f of x plus x. So why waste time on learning this extra thing when we can only learn this? Does that make sense? It's a very simple way to think about this. Now, if has anybody ever done something like linear regression, but let's say hierarchical linear regression? Have you ever done curve fitting? So this is actually an idea that was popular in prior to being used here in other field, and I did stuff like this in my. So let's say you have a signal and you want to really smooth that signal, right? You want to be you want to smooth that. You have an image and you really want to smooth an image. Let's say you're using Photoshop, right? Everybody has used Photoshop or its open source counterpart GIMP. For us, in Nepal, everybody gets the pirated copy, so it's not a problem. But when I was in the US, I was afraid to download a torrent, so I had to use the open source GIMP, but it still works pretty well if you're not familiar. Anyways, I once got a warning from FBI for different reason, but let's not get into that for downloading stuff. But yeah, anyways, since then I stopped. But yeah, here nobody cares. So maybe you all use Photoshop, but I mean Photoshop. Anyways, point being, let's say you want to blur and smooth an image. I mean, this is something what I would do. Okay, maybe I would start with like a large brush, and maybe I do like sort of light touch up, light smoothing all over. Maybe the ladies here are familiar when they do their makeup. You start with like a big brush and you do like, I don't know, like a large contouring, whatever. In Photoshop, the same thing, right? Then wherever there needs to be more finer touch up, you go and then like work with a finer brush on that area, that specific area, right? So it's this idea that in the beginning, the first pass, you do a coarse estimation. You do like a very smooth. You take like an applied globally. Then you take the residual, and then wherever is necessary, you take like a finer brush and you apply it there. So again, I don't know, maybe this is just confusing everybody too much, but essentially the idea is it is not understood. Maybe it is understood in the other context, non-neural network context, um, exactly why this is so, but it is well known that it is a well standard practice in other domain that was borrowed here, where first you do a coarse estimation and you predict the original function with the coarse estimation. Then you subtract the estimation from the function and you estimate the residual, and then you add the residual to your prediction. Then you do it again. You keep repeating this. This is a well-known algorithm. And I used to do stuff like this for like fitting and smoothing, but not using neural nets. So it's the same idea borrowed here. Yeah, makes sense. Are we clear? Any questions? But the cool thing was this turned out to be really this was definitely one of the coolest breakthroughs, and it was cool for two reasons. One, it produced really good results. You can see here the test error is actually it's flipped from the training to test. But in test, the 34 layer ResNet is better than 18 layer ResNet, right? We obviously care more about the test. Yeah, so this is quite impressive, and it's another reason why it's really impressive is that it's such a simple change. You really don't have to do anything. In your when you're using TensorFlow or PyTorch to make a residual connection is so easy. You don't. It's one line of code and no extra parameters. It's the same. The complexity of optimizing this is the same. There's no. It's like this was definitely one of the most exciting idea, both in terms of how good it worked and also how simple and elegant it was. It's very rare where that both of these things happen. Yeah, and this paper I think has like 100,000 citations. It's crazy. um, cool. The next one is I want to discuss is this thing called GoogleNet. I think GoogleNet probably came before ResNet, but I wanted to introduce you all to ResNet because that was such a neat, nice, like this thing called residual, and it was, I think, really nice thing to talk about and simple thing, simple idea, and that's why I talked about this first. So this GoogleNet came before, and GoogleNet has no residual connection. These days, many networks, it's become standard to use residual connections. But yeah, so in GoogleNet, there are a few interesting aspects of this network. One, I mean, don't be fooled by the shape. It looks kind of like weird, like slanting, towards the left. It's just the way it's drawn out. It's still like a sort of this hierarchical setup with layers stacked on top of one another. But the crux of the model is here in the. Let's start looking on the left side, A. So what happens? What GoogleNet does is it does on each output of each layer, it does one by one convolution. Anybody knows what one by one convolution accomplishes? Sorry, scaling. Yes, it multiplies by a constant, but it also averages across well, it does have weights across the channels. So yeah, it does do that. Yeah. Um, you have your 3 by 3 and you have your 5 by 5 as well, with the idea. And why, and can anybody think why are there multiple scales of convolutions here in one layer, in a single layer? So essentially what this is doing is, instead of taking having filters all of the same size, it has some filters of 1 by 1, some of 3 by 3, some of 5 by 5. And here it doesn't even do any filtering. It only does max pooling, but with stride of 1, as in by no dimensionality reduction, because if you do dimensionality reduction, you cannot concatenate, right? All the outputs of these have to be same to be able to concatenate. So can anybody tell me why they think this is a good idea? Yes, no, yeah. Any guess? So what does what would be different between a 3 by 3 and a 5 by 5 convolution? The 5 by 5 convolution has a larger, yeah, it looks at a larger region, right? Maybe it will extract features that are relevant, that are, it's looking at slightly larger area. So essentially, yeah, this 1 by 1, 3 by 3, and 5 by 5, it's trying to create features of different complexity and hierarchy in the same layer. Previously, with the same, only the uh, previous networks until this era had this idea that in the same layer you should only have features of the same complexity, same, like like hierarchy. But this sort of was done so that in the same layer you will have features of different hierarchy and complexity. Because in the first layer, obviously not much is happening, right? In the first layer, it's just 1 by 1, 3 by 3, 5 by 5. But in the second layer, maybe there's advantage of combining the 1 by 1 with the 5 by 5. Maybe there's advantage of combining the max pool with the 3 by 3. We don't know a priori. So what they're doing is they're like mix maxing all these feature types uh, uh, to accomplish much even bigger diverse set of features, and with the hope that these diverse set of features will be even more representative. And that's always the idea. You want to create even and more interesting features. And how to do that is, this is one of the approach. What they do ultimately actually is, because it's really expensive to do a lot of these 3x3 and 5x5 particular convolutions, they first do 1x1 convolution and do dimensionality reduction, and then do, now can anybody tell me again, how would you do dimensionality reduction with this? Any idea? So let's say the previous layer had 256 channels, 256 features. And let's say we're saying, oh, 5x5, it's too much. We cannot do 5x5 on 256 features. Maybe we do 5x5 only on 64 features. So what would you do here? That's certainly a good idea, but well, you wanna this dimensionality reduction idea to be part of your network, right? You cannot pause your training, do a little bit of principal component analysis here, and then come back and do this. I mean, that it would. I mean, you could do it, but it would take forever to train, right? You would never complete. You'd be old by then. So that's probably not a good idea. So you're learning to, but you're kind of on the right track. You're learning to do that dimensionality reduction. What is dimensionality reduction at the end of the day? It's a projection, right? It's a projection from high dimension to low dimension, and these neural networks, these weights, parameters, that's all they're doing all the time. They're doing projections from, sometimes it's from high to low, it could be from low to high as well. We don't know. Sometimes it goes from low to high. So when you use 1x1 convolution, and then let's say you have 256 here, then what you can do is you can take 64 1x1 convolution filters, and it will collapse that 256 channel feature to 64 channel feature. And then you can do 5x5 convolution. Why would you do that? Because it significantly reduces the amount of computation you have to do and the number of parameters. It would take forever otherwise. I mean, yeah, makes sense. Is this part clear to people? The idea that you want to have diverse set of features representing different hierarchies, and you accomplish this by doing dimensionality reduction. Otherwise, it would take too long. And oh, it even used 7x7 convolution, which is crazy. I've never seen this that much these days. In the very beginning, just the very beginning, the first time, and then it never does it. Oh, it has another interesting concept called the auxiliary classifiers. Let's go back here. Do you see there are three outputs of this model? There's this one here, and two here, and three here. And all these outputs are actually tied to the same output. It's still predicting the same thing, but at three different places. And yeah, it's still predicting the same thing. And there's a loss function associated with all these three as well. And but the main one is this, but the losses for this are also added to the main loss. Now, why would you think this would be a good idea? Why do you think they did this? Anybody has an idea? It again has to do with training and optimization and gradients, right? So the idea is, because oftentimes, the gradients are actually really good here in the top because it's closest to the output, right? And the gradients actually vanish when you go back. That's back propagate. That's what the word means, right? You go from the top to the all the way to the just the last of the first layer, but your gradient always starts from the top. So the more back and back you go, you may start having difficulties with good gradients, and you need good gradients to do gradient descent. That's why they thought that they will stick these losses in the middle as well, so that the outputs are close, if not to the main loss, these like auxiliary loss, these like secondary and tertiary losses, and it helps with the training. Does that make sense? in the end, these two are discarded and not even used. When you doing inference, only this one is used. All right. Yeah, so GoogleNet was before ResNet, and before they came out, their performance was pretty good. I mean, but yeah, I mean, I guess they were the best in the year they did. So they had the top 5 error of just 6.67%, and that was crazy. And I think I don't know if the goalpost, if the idea has changed from then, but I think they used to say that back then, like 5% was like sort of the target. Again, human would make like a 5% error, maybe on, I forget if it was the top 1 error or top 5 error. I'm not 100% certain, but maybe it's the top 1 error. Sorry, but if anyways, there was a human level sort of benchmark as well, that there was an idea, and I think it has already been surpassed or equaled by now. But back then, this was quite impressive. Yeah, and I mentioned VZZ before. Back then it was like really popular, but this Google, I don't know if I have that in table, but the GoogleNet was so much smaller than VZZ and so much better. Well, not so much better, but better. But it had, I think, like 10 times less parameter. Now the last one, and not my favorite, but the one I used for the example earlier, and hopefully you will do in the lab today. And I actually also use this at work, because at my work we try to develop applications that can be deployed in like mobile tablet platforms. So we need really lightweight networks. So that's why we use this. And the mobile net has one really simple idea. It's this idea of taking your standard convolution and then factoring it out to this called separable convolution. So depth-wise convolution and one-by-one convolution. So this may be slightly, so let's see how this, I mean, I'm going to try and explain how this works a little bit. So in a standard convolution, you have we saw this earlier, right? 3 by 3, and let's say the channel is 64, which means 64, it means 64 means the previous layer had 64 outputs. So when you want to apply this to the previous layer, you would then, let's say for one of these, you would have to do, let's say that it would be like 3 by 3 times 64. Well, what is the size of the image? Let's say the image size earlier is I don't know, 112 by 112. So you'd have 112 by 112 times 3 by 3 times 64. Now, for now, let's ignore the bias terms. But what the separable convolution does is it kind of like factors this out, right? And this we see this done in like the standard, not just depth-wise. The spatial convolution can also be separated out, right? Because we know that. So the idea comes if we remember our linear algebra a little bit, matrix multiplication. Let's say you have a matrix, right? You have a n by n matrix. You can construct, and there's this idea that you can construct a n by n matrix by multiplying a 1 by n, n by 1 times a 1 by n matrix, right? If you take a inner product of a two inner product, there's a dot product. If you take a dot product of a n by 1 matrix and n by 1 matrix, you get what? A singular value, right? But the idea is that if you take an inner product, you get a n by n matrix. It's the opposite of dot product. Are we familiar with that idea? Sorry? Outer product, sorry. Dot product is the inner product. I don't remember terms. That's why I'm not a teacher. But anyways, outer product, inner product is the dot product. But yeah, it's the same idea. So what is the rank of a matrix that you construct using outer product like that? Huh? Yeah, it's actually, yeah, I think, did somebody say 2? Huh? Yeah, I think exactly. It's a much lower rank matrix. Maybe it's two or yeah, it's two. And if it's this, in fact, if it's the same matrix, same vector, and you take the outer product, then the rank is actually one. So it's the idea that a lot of times in these convolutional kernels, maybe the idea was that maybe you can basically you're doing dimensionality reduction, and the idea of this dimensionality reduction is maybe the matrices are actually really low ranked, uh, and you can approximate the full n by n matrix sort of by these low rank approximations. And I think there's like a whole field of research on this, like I think it's like non-negative matrix factorization or something. There's a whole field, but here it's sort of mimicking and borrowing idea from here. When you're doing these separable convolutions, instead of doing the full convolution, first you do just a 3 by 3 uh, convolution on the spatial on the feature, but you don't multiply with n sorry m the across the 64 features. Then you just have, if there are 64 features, you just get 64 features again. And then you expand out that 64 into, you're basically doing, now you're doing dimensionality increase. You're like projecting this into whatever you want m to be. Actually, well, m, well, no, sorry, this m is the same m, but now you yeah, now you then expand it out like that. So essentially, yeah, this is slightly complicated perhaps, but yeah, overall the idea being it's borrowing ideas from matrix factorization, and you're basically assuming these conditions about matrices. But this reduces number of parameters by 8 to 9 times, which is pretty cool again. Again, well, if you look at reference, the VGG16, which is a really old reference, but this MobileNet is like, compared with VGGNet had 138 million parameters. This had 4.2, but look at the difference in performance. It's negligible, right? Look at the number of like multiply and adds, which is basically, number of the amount. This determines how long it would take to execute this and run this inference. Significantly less as well. So it's quite impressive that this tiny model, and the mobile net can I don't know if I have that in the next slide just to wrap up. So the model itself can be customized. The APIs, they allow you really nicely that you can make the mobile net like shallow, I believe, and also the resolution with multiplier. Yeah, you can make the network like shallow, like remove different layers. You can change the width. Probably width changes the number of features. You scale the number of features, and you can also change the resolution. It could be 224 and different. And you can, well, there are different trade-offs, obviously. But let's say for a small reduction in the width, the number of features, there's not a big change in accuracy. Similarly, small reduction in resolution, not a big change in accuracy. Again, all of this suggests this is pretty cool. Yeah, that's it. Oh, okay, last topic was here. I'm not going into these topics. These are just advanced topics for you all to ponder. Maybe other readers will get into, other speakers will get into these topics in later sessions. But one really cool topic these days is one shot or few shot learning, which maybe we have heard about it already a little bit, or somebody else will go into detail. My favorite is YOLO because the name is so cool. Yeah, YOLO for object detection is a pretty cool algorithm and very popular these days. The previous best was this thing called RCNN, and it was slower and very clunky. And this YOLO made it possible to have much faster and also pretty accurate object detection to draw these bounding boxes that I mentioned that you need. And attention mechanism. These days, there's a lot of a lot of models use attention, and it's pretty cool. Attention can be both self attention, and you'll hear terms like this: self attention or not self attention. Like And there are these thing called transformer networks, which actually use a lot of attention. So it's just like a next iteration of these attention ideas. These are used even more so in natural language processing, and maybe somewhat less in computer vision, because convolutional networks work pretty well, and the transformer networks are really big and large, hard to train. Not hard, but it takes too long right now. But but there have been work that already shows that you can use transformers for images as well, and the results are pretty good. Cool. All right, that's it for me for now. Any questions? I think people are tired, want to eat lunch. Remote people, any questions? So was this idea clear to you? Anybody not understand this part? The idea of separable convolutions? Maybe I'll ask another question, which is, so models that came after GoogleNet had another way of having features of different hierarchy at the same layer. Can anybody tell me what that strategy would be? Anybody knows UNet, for instance? Who knows what UNet is? Who has seen a UNet architecture? Nobody has seen the UNet architecture? Okay, fair enough. Then that's, sorry, my bad. So actually a lot of models, they don't do this sort of thing anymore, because instead of having these different convolutions and stuff at the same layer, what a lot of modern models do is actually concatenate features from previous layers onto the current layer. This way you can have, in the same layer, you can have features of different, like, complexity and hierarchy. And that's how this one particular network does it to the extreme. I think it's called dense net, where at every output it concatenate everything it has seen so far, all the outputs so far. I mean, that is probably certainly a little bit extreme, but still it happens. Yeah, that accomplishes the same task, and people still use, I think the residual idea is still used quite well and still quite powerful. Yeah, that's all for me. I would like to end here.
Hello. Thank you, Nripesh. So CNNs are currently the workhorse of most of the deep networks, especially for imaging and computer vision, right? And thanks a lot, Nripesh, for talking about CNNs. I think he won't get opportunity to talk about his other works. He does some really amazing work in medical imaging, working in a company like Capson Health, which is getting quite big, working on ultrasound, so that building systems, deep learning based systems, where they provide automatic guidance to human operators who could be non-experts to use ultrasound for, especially in cardiac diseases. He's working on and doing some really amazing work. I'm not sure if Mahesh, others were able to introduce you. So if not, maybe we will introduce. Yeah, they already know. Otherwise, perhaps you get introduced more in the lab sessions. We have lab sessions, right, at night in CNN. So I hope you will get more insights about these topics later tonight as well. And I would really like to thank Nripesh for making out his time and coming here and giving a talk. And we would like to appreciate with a token of appreciation with Danda Pani Paudel will give you. Let's give him a big round of applause again. Thank you. Thank you. Now let's go for lunch. Okay.